So good morning, ladies and gentlemen. It's my great honor to be here as a first speaker. So I decided to start with a short video that will somehow motivate my talk. So the title of my talk just was is in the next slide. So we will go to the presentation. So you see that there are actually three topics covered by the title, as Radko Messial already mentioned: fuzzy transforms, Bayesian networks, and they both will be applied together for analysis of data collected in sociology analysis, sociological analysis. So I should thank a project that is funding us and funding me also, which is a project of Ostrava University, where we try to apply the theory to somehow help with new technologies in the energy sector in the Ostrava metropolitan area. So this is the first part of the talk where I start with the potential picture of Reverend Thomas Bayes. His picture actually is not known, so it can be anything. It could be also this picture, which is most commonly used also in Wikipedia. You can find this picture. And this person lived in 18th century. And actually, during his life, he was not known at all. When he passed away, that his relatives invited Professor Price to visit them, and he found actually some documents. And after that, they were presented by him in the Royal Society in England, and he became famous. But actually, he didn't know that he is going to be famous. And what he is famous for is here. It's a Bayes rule. Bayes rule is probability of event A given B is equal to probability of event B given A times P, prior probability of event A, divided by probability of event B. So these are events A and B. This is the conditional probability of event A, that it will occur that B is true. Then we have the reverse probability, and these are the marginal probabilities or prior probabilities without any conditions. Okay, so this is the theorem. And I decided just to explain it using an example probably all of us know very well. Uh, it's not so far away, but fortunately it is already history. It's not so much with us anymore, but still the virus is here, but the problems are not so serious anymore, fortunately. So I will use this as an example. So now my variable C will denote presence of COVID. So it will have two states, yes and no. Then I have prior probability. So it could be considered as a population prevalence of COVID in the population that is tested by that. So it could be much higher than the general population. Maybe you already feel bad. So then you decide to do test. Otherwise, this would be terribly high number, 2%. But okay, let's consider this is just for the population that's going to be tested. And then I have the positive antigen test result, which can be true or false again. Then what is actually written on the box is this number. So you have written sensitivity of the test, which is exactly this conditional probability. So assume you have COVID. What is the probability that the test will be positive? And you see it is 44%. So these antigen tests are not so reliable as, for example, were the other tests that were used. So 45%, important number, which will play a role in what I am going to say later. And we have specificity of the test. That's the second number, which is usually on the box, or you can find it in documents. So it is what it is. It is assume you don't have COVID. So what is the probability the test will be negative? And this is pretty good. It's 99%. So there is only 1% chance it will report COVID if you don't have it. Looks good, but now assume you get positive tests. So how can we compute the probability you have COVID? This is exactly Bayes' rule you apply. Okay, so here the colors corresponds to the numbers we have. You see, I have directly here the pink one, I have green one, but I don't have still the PT. Okay, how can we compute it? It is in this way. So the PT can be computed using these four numbers, blue, red, and green, together in this way. So it's actually that you sum over two possibilities together to get to PT. Okay, so now you may guess what will be the result. Now I assume that maybe we can use the time just to play a game. Who thinks it is more than 90% that you have COVID? Please raise your hand. Okay, nobody. Who thinks it's more than 50%? Please raise your hand. Oh, not many. Okay, so who thinks it's less than 50%? Well, oh, great. Oh, great. You are right. But it's not so much less than 50%, it's 47%. Okay, so this somehow explains that why when you took the test, it couldn't be say for sure you are having COVID. And it's if you think about the formula and you try to analyze, you come to this conclusion that this is not so surprising. Okay, so now we can use a Bayesian network to model this. This is very simple Bayesian network, which has only two variables, COVID-19 and antigen test. And of course, they are related, so we connect them by edges. And now we can play a little bit with this edge, with this model, where this edge actually denotes the relation, and there is a conditional probability, which we have to attach. We attach prior probability to this node and conditional probability to this node. But we can extend the model, and it's now becoming more interesting with the second independent test. So we have this variable, which is connected to with first test. And if we do it on the same person, second independent test, we can build model like this. And now we can play with it. And I will play with it using these screens, which illustrates what are the probabilities for these variables in the model. So assume we don't know anything. So you see here that the person has 2% probability he or she is having COVID. Now we enter the information. So we condition on first test, and we get this number I already reported. This is this 47%. And now I will do the second test. And now I will not play this game again. I might ask you to guess, but you will see the result. What's that link? Yes, good. So now what we can see that after we enter the information about the second independent antigen test, it goes from 47% to 97%. And maybe you remember from COVID time that there was a recommendation. If you take antigen test and your test is positive, take second one. And if also the second one is positive, then you are pretty sure you have COVID. So it is illustrated by this model, which uses Bayes rule. Okay, so we may play with this model once more, and now assume we know that person has COVID-19. And we can enter the result of the test. And you see, it doesn't tell us anything about the result of the second test. You know why? Because we know that the person has COVID. So there is no additional information added to this information by making the test if we know the person has COVID. So we can say the first test result is independent of the second test result given the status of COVID-19. So we come now to the concept of conditional independence, which is actually encoded in this Bayesian network. These two variables are independent given the third one, which is the parent of both of them. Now, a second example, which will illustrate the different concept, which can be also modeled. Now, assume you have two diseases that cause one symptom. I have example of flu inflammation causing fever. So they both can make you to have fever. So the model is like this. Now we have some prior probabilities again, and the prior probability of fever. And now assume we observe that flu is positive. Does it have an impact on probability of inflammation? Not really. There are independent diseases, so this is how we assume it is. So we can say flu is independent of inflammation. Maybe it is not true from a medical point of view, but I couldn't make better example, but I assume it is like this. But the more interesting thing is what happens if we observe that a person has fever. Okay, now we know a person has fever, and now we make a test which will say that the person has flu. You see what happens with inflammation, which is another cause of fever. It goes from 30% positive to only just 5% positive. Some people would say, "Oh, this is strange, isn't it? Because now we decrease the probability." But if you think about it carefully, it is actually not counterintuitive because you have two causes and you rule out one by saying it is the second one, or it is the first one and you rule out the second one. So actually, this illustrates that flu gets dependent on inflammation given fever. So we actually the possibility to make things dependent by observing something. So this is the second property of Bayesian networks, which is important and it has many applications. Okay, so now I mentioned definition, and the definition is formally like this. So Bayesian network is defined by directed acyclic graph whose nodes corresponds to random variables and the joint probability distribution over these random variables. And this is how the formula is built. So we have to have a notation for parents of each node. So this denotes parents of node xi. And if we want to compute the joint probability distribution, it is exactly product of all probabilities, conditional probabilities for all nodes. So always this is conditional probability of xi given parents of xi. So here is an example, which I will use later again. So we have a Bayesian network which has 3 nodes in the second layer, 1 in the first, and they all have the same parent. So if we use the definition of the Bayesian network, we see that the joint probability of these 4 variables is computed as a product of A15 given D11, and so on, always the parents. And D11 has no parents, so there is no conditioning part. So now we got the definition of Bayesian network and an example. So now let's go to the second part. So this is what I think should be the picture for fuzzy sets. Okay, I could make a better one, but yeah, maybe this is the AI decided to call it dizzy. So this is dizzy representative of fuzzy sets. So now maybe I could rather let Irina speak because this is her topic, but I will just briefly go over it. I hope I will not make any serious mistakes. So now and probably you all know it better than me. So fuzzy set is a pair where U is a set and A is a mapping from universe to interval 0, 1. We refer to it as a membership function. In this work, the universe U will be only the interval of real numbers, AB. And an observation of a random variable X, where K is a value from the Likert scale. I will apply it to sociology data. So I use just variables that have states from the Likert scale, and Likert scale usually is a set of some integers, typically from 1 to some number n, which is either 5 or 7. And it can be interpreted as a fuzzy set. So here we have notation for that. and a family of fuzzy sets where n, the small n, which is and will be typically in our application less than the capital N, so small n is smaller than capital N, will be the family will be if they are defined in the same universe, it will be called fuzzy partition. So here we have some example where the AK are Gaussian distributions. And here is the picture when we sum them all together. They don't make it all one together at all points. They actually, there are some values that are different. So this doesn't satisfy the Rospini condition, but we will have some other ones that, for example, p-curves, they satisfy Rospini conditions. Triangular basic functions do as well. So, and another example are trapezoidal. So we can think about these that do satisfy Rospini condition. Okay, so now the definition of fuzzy transform, which is defined like that we multiply. Now I will transform a probability distribution using these fuzzy sets, AK. So I always multiply the value uh, with the fuzzy set function, sum over all of them, and then kind of normalize. So you can think about it as a product of the probability distribution at these points by a normalized membership function, basic function. And if we just make notation simple, if this is denormalized with denoted by tilde, we can write it like this. So it's kind of weighted average. I think it's always better to illustrate it by picture. So before I come to picture, I just use matrix notation to denote the same. So here it is written in the matrix notation. So we have somehow we can conveniently use the standard matrix product. So we can write the whole formula like this. But it's actually the same thing as before, just using matrix notation, which I like because it's more compact. So, and now the promised illustration. So now assume we want to compute fuzzy transform. So this is our marginal probability distribution over all these 7 values. So this histogram, the gray columns, illustrate some distribution. We did it for data that, for example, there were people ask about if there was a referendum in Czechia about leaving EU, how would you vote? And this is the result. So column 1 is that people would leave. Column 7 is that people would stay. 4 is that they don't know or they are neutral. And these are like weak statements, like probably leave or slightly leave. And here is rather stay. So you see there are a little bit more people that would like to stay. There are less people that would leave, but still these numbers are not so different. And there are some people that don't know. And now I want to transform this using F transform. So what I do here is the first basic function. This is the red, and it's Gaussian in this case. So these points corresponds to the values on the Likert scale. So I multiply them always together. So the black dot is multiplied by the green by red dot. Here. These are zeros. So we just get 2 values and then we sum them and we get this U1. Now, how we get U2? So now it's the second basic function, the blue one. So we multiply it again. You see that we multiply here the blue with black. And again, we get number U2. Third, again, fourth, U4, U5, U6, U7. And in this way, we get a vector of 7 values. This is the case where actually the capital N and the small n were the same. So I allow that case. But typically, we will have the small n lower than capital N, which would mean that the vector is shorter than the original values. I just did it because I wanted to compare the original with the transform one. And we can do it using inverse of transform, where we try to get back what we had at the beginning, and we can observe how it is. So again, we can use matrix notation for this. And then we start with uh, this representation where we get using F transform, we get this U. But the interesting thing is that now we can extend it to a grid which is finer than the original one. So we can actually get it to almost something which looks like a continuous. And we can do it on a finer grid without problems if the basic functions are defined also on other numbers than these 7 numbers we had at the beginning, which typically is no problem at all. If you have Gaussian, it's defined on all intervals. So, and this is how it looks when we get it back. So actually from the original histogram that we had, we get back this curve, which is actually a mixture of Gaussian distributions in this particular case. To compare it, so this was the original we started, then we applied F transform, then we applied inverse F transform for the full interval, and we get this curve. So this is how we can actually represent functions in a nice way, which I like, because we typically have quite some problems when dealing with continuous variables, and this is, in my opinion, quite a nice way how we can represent them. And the other important fact is that the number or the length of the vector can be shorter than the original, actually marginal, which is another benefit we get. So, and now interesting questions comes, because I already, I was speaking only about one-dimensional transformation, but we can actually make it any dimensional we like. Now we have d dimensions, and we can do this transformation using F transform for many dimensional functions, not just for one dimensional. And this is how we can write it. And it's using now we have these are matrices, these are tensors, which are just many dimensional arrays. So it's like generalization of matrices to more dimensional spaces. And this is a special operation which is called mode K, tensor matrix product. I will not go into details, but this is somehow um, that you try just to replace in this tensor, you replace one dimension using this product, then you continue to the second one, third one, and you always operate with one dimension. And at the end, after manipulation with this tensor, you get the tensor U. And then you can do the inverse F transform. And when we write it down and look at what it is, actually the above formula is the Tucker tensor decomposition, which is quite studied in the tensor analysis. And this is really good news. I didn't know this, but actually someone who would work with tensors would immediately see it. And for me, this is quite nice observation that can bring some benefits for us. Okay, so how would look this in 3D? So you can imagine this Tucker tensor decomposition as something like this. So this is the original 3D tensor, and you will replace it by a small 3D tensor, which has this N1, which is smaller than N1 here, which is capital N1, N2 smaller than this one, and 3 smaller than this capital N3. And you multiply it in each dimension by a matrix, which is called factor matrix, which has dimension always the small n and capital N. So you, by multiplying it in one direction by this, in the other direction by this matrix, and in the third dimension by this matrix, you get a tensor of this size. But here is this wave, which is, it's similar, it's approximated by that. And the question is how well we can approximate it. Okay, so now I come to the third part, which is the application part, sociology. So we had the data set, which was data set called Dividing Lines in Czech Society. And the data set was prepared by STEM agency. Maybe some of you who are Czech or Slovak maybe also know the STEM agency, which is like one of the large agencies that does surveys. And they collected opinions of 1,661 Czech citizens. They were very careful in selecting people for these surveys, so it should be representative of the whole populations. They think about gender, age, education, all these things when they collect the data. And this was summarized in a publication by Martin Buchtík, who is the head of STEM, published in 2023. And in Czech, it's called Různá vyprávění o jedné společnosti, different narratives about one society. And the response format was that they responded on 30 key topics of public life, denoted by A1 to A30, 14 assessments of one's own life situation. So they also reported something about themselves. And then they were all reported using Likert scale. So it is the ordered scale from 1 to 7 in this case. So the medium point is the mean is like the point where you say I have no opinion or I am neutral is 4, and these are like extremes are 1 and 7. Okay, so this is just to illustrate what we get when we apply some standard algorithms for learning Bayesian networks to this data. And there are different methods you can apply. You can think about like testing conditional independencies and adding edges so that the conditional independencies are satisfied. Or you can take machine learning approach where you try to maximize some criteria that best explains the data. And this was the approach I took in this which is so-called Bayesian information criteria, which is a criteria that somehow tries to fit data as best as it can, but also considering the number of parameters. So it's like penalized log likelihood that is used for learning this model. The nodes are positioned by Fruchterman-Reingold algorithm so that those nodes that are correlated more closely than the other tend to be closer to each other. So you see that some nodes are far away from the others. So this is like the opinions that are not so much related to these other ones. And the last thing I would like to say that green nodes corresponds to assessment on their own life, and the like yellow nodes corresponds to the key topics. So you see that there are some like opinions that are not really much related. The assessments of their own lives are not much related to their political opinions, but there are some that are related. And this is very interesting for sociologists to see what actually are those that are related. And maybe we can think about like if we want to change an opinion, whether we should somehow try to, for example, improve the economical situations of person that we so somehow this may have impact on their opinions or vice versa. It could be as well that, yeah, but typically, usually it is not. Okay. So, for example, we can see what are the more central variables. And for this, we have in Bayesian networks concept, which is called Markov blanket. And it's based on the analyzing the neighborhood of some node, how large it is, for example, if the size of Markov blanket is large, it means it is very central variable that is related to most to other variables. So actually, the most related variable was the question about referendum, which has 11 neighbors. Then the trend after 1989, which was the Velvet Revolution, in that time Czechoslovakia. We had 8 neighbors for this. And you see that somehow most interesting assessment of her or his own life is trust in future, which is something which somehow makes impact on your political opinions as well. So, and then benefits of EU, that's the 11, which has 6 neighbors. Okay, we could do a lot of things with this Bayesian network, but I think I cannot speak more about it because it would take too much time. Okay, so instead, I decided to show you this picture, which is somehow a representation of one probability distribution I selected from this model, which is D11, A15, A18, and A19. And these are actually, this is actually a matrix of matrices. And in one dimension is these rows, the other dimensions are columns, then the internal rows and internal columns. So in this way, you get these 4 dimensions. This is one way how can you visualize 4-dimensional array. It's actually tensor. This is a representation of a tensor. So you can feel what it is. And you see there are many zeros there. So of course there are many zeros, because if in data we have 160 respondents, and this is even similar size, the number of fields here is almost similar. So you cannot have many non-zero or at all non-zero entries. Okay, so I have maybe a better visualization for you. At least visually, it looks better. And it's the same tensor represented in graphic, and the colors corresponds to the states of the last variable 819. And then the size of the rectangle is corresponding to the value. So if it is more probable, then it is larger. And you see there are 2 big rectangles in the corners, blue one and red one. Yeah, so these are like there are some correspondences between opinions, which are rather negative of all or rather positive of all. And there is this central people that have neutral opinion on anything. Maybe they were afraid to say anything, but yeah. So this is actually another way how to visualize 4-dimensional tensor. And I must say, I like it more than the previous one. I don't know what you think, but maybe this is better. So now let's look at another way how we can address this small table. We can build a Bayesian network for that, which is actually, in this case, D11, which is parent of A15, and 819, and 818, and 819. You maybe already remember this one because I use it as an example a few slides before. And now they have interpretation. So these are personal benefits from EU, whether Czechia should be part of Western Europe or neutral Britain, whether we should say in referendum leave or stay, and what is the trend after 1989, right or wrong. So if we learn it from the data, we get this model. So somehow this variable personal benefits from EU somehow mediates the relations between these 3. Okay, so this is a subnetwork. I will play a little bit with this, and then probably I am almost over time. So what we can do is now we can look at these conditional probability tables, and we can use F transform on them. And these are the representation we get if we reduce the grid from 7 times 7 to 3 times 3. So these are like relations between geopolitics, and here it is personal benefits from EU. You see, it's always here on the vertical, and on the horizontal, there are these 3 variables A. Yeah, these. So this is what we can get if we apply F transform to them. And as I said, we can transform it back to continuous space. And if we use Gaussian core basic functions, we can get something like this. So this is a visualization which uses F transform to go to the EU representation. And then we get back using this Gaussian basic functions. So in this way, we can like have it in continuous, almost continuous. Okay, so this is how it looks. And then last thing, I mentioned that we can see that we can observe if we go to more dimensions that actually it corresponds to a Tucker decomposition, Tucker tensor decomposition. So instead of trying to use some predefine basic functions of F transform, I let the algorithm to decide. I let the tensor I use some algorithm which is actually alternating least square algorithm, and I said to the algorithm, now you have a tensor, and please apply this Tucker decomposition to it, and let me report what actually what functions you find. And these are the results. I must say you have to do one more thing, because if you let the algorithm do whatever the algorithm likes, then you can get crazy functions that can look weird, like going up and down and up. So the key is to use unimodal. So you require that each basic functions you learn must have one mode only. So it is like going up and down, and not going up and down, up and down, and up and down. So this is somehow restricting the tackle decomposition. And these are the results. If I said that these small ends will be free, 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 and two, to have it a bit interesting, because I wanted to have like not everything. I wanted to show that not everything must be the same. So this is just illustration. If this large dimension will be reduced not from 7 to 3, but from 7 to 2. And this was learned. I didn't intervene into it. This was learned automatically by this ALC algorithm. This is how looks the core tensor. So this is like this small box in the middle, which somehow represents the relations now in the compact way. It's much more simple than the picture you have seen previously. But you see again, there is this big rectangle here and another big rectangle here, another big rectangle here. Somehow the similar representation, but much more compact. And this is if we combine the marginals of the, like, if we project into one dimension, in one, because we have 4 dimensions, so we have 4 pictures. And the blue ones, the blue curves are the original marginals. And these red ones are those computed using this unimodal Tucker decomposition. And you see, they are not so different. And actually, I use much more compact representation for that, but the marginals I get are not so much different. They are pretty similar. And you see, even with actually only a rank of 2 for the last dimension, the algorithm was able to somehow represent it pretty well. And this is the final picture for the comparison. So this was already the picture you have seen. And I must say that this picture needs to be represented. It needs 2,401 values, while this picture, using this Tucker decomposition, I need only 121 parameters. So it's like maybe almost 20 times smaller, but you could see some differences. It's of course it's simplifying the whole picture, but question is maybe it's actually simplifying in the proper way, because maybe people are not so precise in their answers. So this is like behind the fuzzy sets fuzzy sets theory, that maybe you actually use rather fuzzy sets for evaluations than precise numbers. So I would be very careful in saying this is not so good as this one. Maybe this is actually worse than that one, but of course we cannot know because we don't have a way to evaluate it. Good. So now this is the picture that compares the result with the original. And now I'm coming to joining all this together and concluding. They seem happy. I am also happy with this combination. And here is the summary. So Likert scales used in surveys can be naturally interpreted using fuzzy partitions. The F transform can approximate probability tables in Bayesian networks. Unimodal Tucker decomposition can be used to learn factor matrices representing F transform. And fewer parameters imply more reliable parameter estimates from data. And when we do probabilistic inference with these models, it can be much more efficient because we have much small parametric space. And like future application, I would like to mention that we plan to apply to Steneo project data on energy poverty in the Ostrava region, which would be quite natural application. Okay, and then references. So we already published with Honza and Irina a paper at the WPES workshop, and this is about the data case study on Czech society division, which is actually now under review in Kybernetics Journal, and I prepared another paper for RPMU 2026 conference, which will be about this Tucker unimodal decomposition. So that's all. Thank you very much for your attention.
Thank you. We have time for discussion. So please, if there are some questions or comments. uh,
Yeah.
So thank you very much. I am really very happy about these results. Yeah, something was today new for me as well, and I think that it somehow gave second life to the transform theory, who is now a bit restricted, with applications, and I'm happy that the field of applications now is extended, by this. I have one question and one remark, actually. Yeah, the question is about the Tucker decomposition. So, can you give more details? So, my understanding is that you are. So you gave as an input the how to say many dimensional surface, and you made a kind of projection, to axis, or how it works
The
actually.
algorithm works like that. You really start with this blue box,
Uh-huh.
and then you try to find all of these four. So you try to find the core, and you try to find these matrices. And the way the algorithm proceeds, it somehow tries first it initializes these matrices somehow, and then tries to reconstruct the core, which is something which we do actually when we use F transform. So this is like the first step, and then it tries to improve these matrices so that they better fit the P original. And the algorithm does it step by step. So first tries to improve one, then gets it back, and then improve second, improve third. And then it iterates until the convergence, which it tries to fit as best. The norm, the Frobenius norm is used to measure the distance between these two. But there is one hook in it. We don't want to have any metrics here. We want to have some special matrices. We want to have unimodal. And there is actually nice paper about how you can project to unimodal space. And it's actually a very efficient algorithm. If you have a matrix, which is a good approximation. In this case, you can nicely project it to the matrix that has unimodal rows, which is exactly what we like because we can interpret it using fuzzy, using membership, basic functions that are unimodal typically. I think you would not like basic function which has two modes. No, so this is how it proceeds.
Yeah, rather, very interesting. I will probably learn more details. Yeah. However, when you answered, so came to my mind that some machine learning can be applied also,
Yeah, yeah.
because it's typical, machine learning, problem. Yeah. Uh, but my second, actually remark, it will be interesting to see a kind of dynamics. Yeah. I mean, so when you ask people, to answer questions, and you obtain some questionnaire, it was in the year 22, so you can repeat the same questions, after a certain period, for example, I don't know, after
Yes.
2 years, whatever, and then we can compare, their answers, and then we will see how the model keeps dynamics. So
Yes.
this is.
This is an interesting idea. I think, like we can even think about, for example, if you're represented by Bayesian network, whether not only parameters change, but whether also some structural relations change. For example, previously your opinion was related to your personal situation, but maybe after some time it's different. So this would be very interesting, and I think for sociology this is very interesting to see the development in time. Yes.
Right, thank you.
Thank you. So it's very close.
That's why I asked. Uh, my question is not based on a full understanding yet, so maybe you have to clarify some things. The Likert scale is intrinsically ordinal.
Yes,
It's identified with numbers for ease of storing in computers.
exactly.
The same happens with many applications where people have fuzzy partitions on scales that are not continuous. it's heavily criticized by Didier Dubois in many of his
Mhm.
papers that these do not exist. The same here. If you replace the numbers again by labels, um, then the fuzzy partition concept disappears because there's nothing numerically in between the different values.
But still, you can have them ordinal, even if you have labels. And typically, actually, they use labels. They don't use numbers. This is what we do, actually. They use like strongly agree,
Yeah, but
agree.
you build membership functions on an underlying scale. So my question is the following: is this maybe intrinsically another way of learning an underlying scale? Because you want to map like a latent scale that is between different labels transformed in a different way, not exponential or linear. Because if you use a Gaussian fuzzy partition, you'll be doing strange things in between different labels.
I think you hit the point. I really like this comment because this is exactly what I would hope for. Now I learn it, but I'm still not sure to interpret it in this way. But at least I would say I'm going this direction. And if I could conclude it in the way you said, I would be very happy.
Okay, thank you.
Thank you, Bernard. Some other questions or if not? Okay, so thank you, Irka. And we have now coffee break, maybe, but I recall that it's here. And we continue.